In this lab, we observe the motion of an object dropped from rest, which falls vertically in the negative y direction. This motion will be analyzed using Newton's second law that states that a net force that is not equal to zero will cause changes in an object's velocity. A ball of socks has an initial velocity of 0 meters per second and has a non-zero final velocity, so this means that the object will have a non-zero net force. I predict that this change in velocity will cause the object to speed up as it falls. With this, its position versus time graph should consist of a curved line because the object moves a further distance with each incremental change in time. In Tracker, the video of the motion consists of 18 frames, with the change in time being 0.033 seconds between each frame. The coordinate system is set so that the object's initial position is 0 meters at the origin, and the motion is in the negative y direction. The values should be observed to allow us to further analyze the object's movement using a computational model that will predict the final velocity and final position of the falling object using only the mass, initial velocity, net force, change in time, and initial position to analyze the effect of the gravitational force and air resistance on the object in motion. The position versus time data points will be taken from the sock's center of mass at each time step as it falls, with a final position of negative 1.752 meters at the final time of 0.601 seconds. The data does match the predicted model of motion due mostly to the effect of the gravitational force. Since the velocity changes, the net force is not equal to zero, so first, in order to predict the future behavior of the object, we will find the net force. In the first model, we will assume that the only force acting on the socks is the gravitational force, where it is the mass times the acceleration due to gravity of 9.8 meters per second squared, which is found using the equation of the magnitude of the gravitational field near Earth's surface. So using 9.8 meters per second squared and the 0.033 kilograms, the net force, where the gravitational force is the only force, is negative 0.323 newtons in the y component, and this is negative because the force is acting in the negative direction. For the first computational model without the air resistance, the final position of the object is negative 1.772 meters in the y component, which is a further distance from the experimental model of negative 1.752 meters in the y component. These two final positions are close but not exactly the same, and this is because when the net force is only the gravitational force, it is not really the net force acting on the object. In reality, a small force, in this case the force of air resistance, opposes the motion of the object. Here, the air resistance directly opposes the force of gravity, and for this lab, the air resistance will be modeled with a magnitude proportional to the square of the object's speed. In this case, the effective air resistance is minimal, so the constant is a very small value, and this allows the final position of the model with the net force being the gravitational force plus the drag force to be the same as the experiment's final position of negative 1.752 meters in the y component. The motion of the three models are nearly the same. Some differences are apparent, such as the model with the drag force causes the position at each point to be slightly less than that of the model without the drag force. The largest difference is found between the experimental model and the two computational models, and this is most apparent when analyzing the middle data points. The reason for this discrepancy may be because the socks fall in a blur in the video, where the center of mass became more difficult to pinpoint. This could be solved with a more precise fast-motion camera that allows the object to appear more clearly in each frame. Another difference may be due to the fact that the socks are nearly round, but not an exact sphere, which allows the shape to change as it falls, and this could cause a small change in the drag force or allow the center of mass to be incorrectly recorded. All three models depict an object that accelerates with a nearly constant force as it falls, which causes the object to accelerate as it falls. Even with the drag force coming from the surroundings and opposing the object, the force is so small that the difference between the models is very small as well. If the only force acting on the object was the gravitational force, then all objects would fall with the same acceleration regardless of their mass. And this is how air resistance is vital to analyzing free fall, because we know that all objects don't fall at the same speed, and this is due to the effect of their size and shape. And this proves why understanding the effect of the gravitational force and air resistance is vital to understanding the motion of an object and predicting its future position. As an object falls, it continues to pick up speed, and this increases the amount of air resistance until eventually the force is balanced, causing a zero net force and a constant velocity. Consider terminal velocity. In this lab shown in the velocity versus time graph, none of the models had reached terminal velocity yet because the velocity was continuing to change during the period. If the socks were thrown down with a large enough force, then the model that shows the effective air resistance would reach a terminal velocity, while the other one that only shows the gravitational force would show a velocity that increases infinitely.